Hello everyone, I hope you're doing well. This is Patrick Newberry, one of the creators of this resource from the Binchan Lab. The version of the drug discovery pipeline discussed in this video is geared for those with at least some background in R. Others should refer to our video titled Tutorial for octad.org. This image shows the critical features required to run the pipeline. You'll need control ID, a character vector of column names of an expression matrix, case ID, which is different columns of the same expression matrix. Those will go into creating DZ-EXPR, which is a smaller expression matrix, which will be used to create disease signature. Start by downloading all the required coded data files as listed below this video and is shown briefly here. Go to these two websites and you'll download these two zip files. First, unzip the code and parent. Then, within that, place the data folder, like so. Unzip that and you'll have this data file. Next, open this RStudio project and run all of the lines in installpackages.r. Check this missing packages variable. If it's not empty, it will contain the packages that you still need to install yourself. Once that's done, let's conduct a test using breast cancer luminal A R Markdown. All you should need to do at this point is change this base folder to the parent folder that you installed and click knit. On my new MacBook, this pipeline takes approximately 30 minutes to complete. Errors are most likely due to missing packages, improper file permissions, or missing OS utilities such as Clang or GSS. It's common to need to spend some time troubleshooting these at this stage. When this HTML window opens at the end of a knit, pipeline is successfully completed and you'll know your computer has been properly configured. Now to the real money, setting up your own run. If we scroll down to the parameters chunk, the hyperparameters will be editable here. The only ones we recommend tinkering with are normalized samples, ntop genes, log2 fchange, p-adjusted, choose FDA drugs, and max gene size. The first main step is to establish the case ID vector. You may use whatever method you prefer to accomplish this. Perhaps you've been working on a subset of TCGA or MET500 samples. You could simply enter those here. The second main step is to establish the control ID vector. Again, there are many ways to circumvent the method we're using as an example here. Any method you choose must result in the character vector variable control ID, containing all of the samples you wish to use as controls. Note that we're establishing normal ID, not control ID. Normal ID is the pool from which your controls will be selected. Control ID are your actual controls. Down in the case.load4 chunk, this readies the encoder DF matrix by subsetting only the samples of interest. This matrix will be used to determine which samples from normal ID are most similar to those in case ID. Only samples we include in our original publication will be present in encoder DF. You can add new samples to this with significant knowledge, but generally new samples will be absent. For any samples, old or new, you can alternatively use count data, TPM, or whatever other form of expression matrix to evaluate similarity. Just change this matrix. In the case.load6 chunk, this is where control ID is actually created. That is the character vector of controls that will actually be used to compute your differential expression and your drug predictions. This gets saved as control IDs.txt. To conduct differential expression analysis, or DEA, this DZ-EXPR needs to be replaced by counts if you did use encoder DF. Using the provided data, these lines accomplish that. The next few chunks are validation where controls were selected from. Here is one such output. Using our previously defined log2 fold change and p-adjusted thresholds, filtered results are saved as this disease signature. This gets annotated later and saved as diseasesignature.csv. Drug prediction is carried out by this run srges function. This is perhaps the best example where one can circumvent the pipeline by inputting one's own disease signature. Let's take a look at the CSV. It's important here to note that the only thing that matters from here on out is the sign and relative rank of the genes based on their log2 fold change. Therefore, a disease signature can be easily synthesized. However, keep in mind you must match the format of a normal disease signature like this one. Run srges will take a few minutes to complete. The rest of the chunks in this document are enrichment analyses of various types and visualizations, which are technically optional. However, this one, which is ranked cell lines, is used as in silico validation, which any good investigator is going to demand some form of. For enrichment analysis, you can check the enrichment analysis folder. And for in silico validation against CTRPV2, you can check the cell line evaluation folder. We're happy to help. If you have any questions, please feel free to reach out via email, and thanks for watching.